What's up, TJ Machine Learning Club? My name is Vishal, and along with Arnav Jain, we'll be presenting on the applications of machine learning in cybersecurity. Okay, so just for a quick introduction, we know that web and mobile technologies they're developing rapidly, but that also means that cyber attack technology is also developing. So as a result, it's getting signature-based approaches are failing to work, and the tech techniques are getting better at penetrating systems. So as a result, we need better cybersecurity measures. So therefore, we're turning to machine learning models to help us increase the performance of our cybersecurity industry. And some four of the applications of machine learning and cybersecurity that we'll be talking about today are phishing detection, network intrusion detection, social network spam detection, along with cryptography. Okay, so what is phishing detection? Phishing detection is like when scammers try to impersonate someone or something to steal your personal information. So, for example, when a scammer pretends to be Amazon and sends you a link saying, here's a free $100 Amazon gift card. And they use 6 different models and analyze the error rates of those models. So they use logistic regression, classification of regression trees or decision trees, support vector machine, neural networks, Bayesian additive regression trees, and random forest. So I'll be explaining what a BART is, since I know that we haven't covered that. Okay, so what is a BART? A BART is an ensemble learner. So it uses boosting in that it makes use of a lot of weaker learners in order to make a stronger model. And it uses a prior and a likelihood to get a posterior distribution of our prediction. If you don't know what that means, no worries, I'll be explaining that. It has a built-in complexity penalty, eliminating the need for making empirical choices on things such as regularization, max tree depth, etc. via cross-validation. And the BART outperformed all other tree-based models on 42 different data sets. Okay, so if we look at this Venn diagram, say event A is the probability that Lil Uzi Vert drops an album, and event B is that it rains. Okay, so given that it's raining, what's the probability that Lil Uzi Vert drops an album? So, okay, so event B, it's already raining. What's the probability that Uzi's going to drop an album? It's going to be this blue region, right? Because if it's already raining, then the only place that Uzi also drops an album is going to be this blue region. And we can express this as P of A union B. So P of A upside down UB is just this blue region. And so A occurring, given that B's occurred, is just going to be noted as P of A bar B. So if you look at this formula on the right, P of A bar B, or P of A given B, is equal to P of A union B divided by P of B, since we also have to account for all the other instances where P of B occurs but not P of A. And we can use the same derivation for P of B given A, and we get this formula. And what we can actually do is we can multiply by P of A on both sides, and then we can substitute this guy for this guy. And that's how we get this equation on the bottom right. And also, one thing to note is that the evidence, or P of B, it's just going to be a constant, so it doesn't actually affect the shape of the posterior, since these are all probability distributions, these top 3. And this bottom's a constant, so it won't affect the shape of the posterior. So that's why we don't waste the time calculating it. But if you want to know more about why that works, torresdatascience.com has a great article on Bayesian inference. Okay, so now that we understand this, okay, so what is this? This is actually going to be the likelihood function for the BART. So what this means is that, okay, so for since there's m trees in the BART, for each tree in the BART, we give it an x value and it returns a value. So this is an example of a tree. So if we give it 75, it'll give us 26.2. And then say a different tree, if we gave it 85, it gave us 74. So then you do 74 plus 26.2, which is 100.2. And you repeat that for n number of trees in the BART. And then this E just means extra Gaussian noise or error. So it just means it's normally distributed. So bell-shaped curve, mean at 0, and the standard deviation is determined by this formula. Just know that K is usually 2 and M is usually 200. I'll describe why later. And yeah. And this is standard deviation of that E distribution. Okay, so yeah, this is Bayes' theorem, basically, that we use prior knowledge. So this blue region, we use prior knowledge with, and then when we acquire new data, and we combine what we already know with what we've discovered to get a new updated knowledge, or this green region. So this is just a card tree. Okay, so the authors of the Bayesian of the BART actually discovered that past m equals 200 there wasn't a significant improvement in performance, so they did not see a reason, so everyone just uses m equals 200. And okay, so how do we find the prior of the BART? So the prior of the BART is just going to be, so the prior is going to have to take into account every single component of the BART, right? So the tree, and then this M. So what is M? So M is just the set of all of these gray boxes or leaves of the tree. So all these gray boxes. So it's just going to be the prior of each tree and its set of gray boxes along with the noise. So we can move the noise to its own prior and multiply it at the end, which allows for us to do some more simplification. So we move here by moving the noise to its own prior. Then we can re-express this lengthy thing as just this short function. So what this means is it's just the product. So the product of all the product of the priors of each tree and its corresponding set of gray boxes. So the product of all those priors times the product of noise. And then we can use this formula, which we actually derived earlier, multiplied by P of A on both sides. So we can use this formula to simplify this T of J, M of J, since T of J, M of J is just a shorthand for T of J and M of J. So we can simplify this into this. And then, actually, since M of J is just the set of all those gray boxes, we can simplify the prior for M of J given T of J to the product of all the priors of each gray box given the tree, and you multiply all those priors for each gray box, and then this is the fully simplified form of how we find the prior for the BART. Okay, so first I'm going to start off by defining what a residual is. So a residual is basically the difference between a point's actual y value versus its predicted y value. So in this case it'd be the y value of a point minus the y value of the green line. Okay, so how do we figure out the prior for the noise? So what we do is we get some estimate for the standard deviation, either by taking a sample of the y values and calculating the standard deviation, or we can fit a best fit line, calculate the residuals for every single point, and use those residuals. And then what you can do is you choose a value for v, either 3 or 10. And then with 3, you pick a value for lambda so that either the 75th percentile, 90th percentile, or 99th percentile of the prior is equal to the value we got in step 1. So usually it's the 90th percentile. So what that means is that if we draw a line, the area to the left of that line is going to be equal to 90% of the distribution's total area. And basically what this means is that you just have to choose a value for lambda. So say it's 3.68. So at x equals 3.68, it's the 90th percentile. So that's just what that means. Okay, so then how you find the prior for each tree. So you can use this equation where alpha is usually 0.95 and beta is usually 2. So 0.95 times 1 plus the depth of the node to the power of negative 2. And that's the equation you use. Okay, so step 2, if a node is non-terminal or it's a white box from the previous example, then you want to calculate the probability that each covariate will be the splitting variable for this node. So what that means is that, say you have ages ranging from 35 to 40 and heights ranging from 5 feet to 6 feet. Age will have a higher probability of being that covariate because age has only 6 different split values: 35, 36, 37, 38, 39, 40, while height has 13. 5 foot, 5 foot 1, 5 foot 2, 5 foot 3, all the way to 6 foot. And then once the splitting covariate has been selected, just calculate the probability for each possible cut point that it will be the splitting value using a type of uniform prior. Okay, now so to find the prior for each mean value, so for each tree, we just say that the prior for each mean value given the tree is just going to be the same. It's just going to be a normal distribution with a mean or a middle value of this left parameter and a standard deviation of the square root of this right parameter. So since there's m number of trees and each tree uses this same normal distribution, that means that if we want to calibrate the normal distribution in such a way that it's in the ballpark of the data, what we do is, okay, so there's m normal distributions combined to get this new total normal distribution of the data. So that's why we multiply the u sub mu by m, and it's the mu of sigma squared, but since we're converting it to standard deviation, we've got to take the square root, which is where the square root of m comes from. Okay, so what this k means is, okay, so if k is 1, that means that we're assuming that in the real world, when we give this BART data, 68% of the y values will be between the min and the max of the training data, with 2 standard deviations to the left, 2 to the right. 95% of the data in the real world will be between the min and the max y values of the training set. So usually it's preferred that k is 2. And so now that and it's a system of equations, so we have the min, we have the max, we have m, and we have k. So we solve for these two parameters and we just plug these in to this normal distribution, and that's how we find the prior for each mean value given the tree. Okay, so now that we figured out the prior for the BART and we've defined the likelihood function, so we can use those to determine the shape of the posterior. But how do we use it? So what we do is we use a Metropolis-Hastings algorithm. So basically we generate a sample from the distribution, and that consists of, so we pick a tree from the BART, we morph it randomly, doing things like pruning or growing, for example, and then we sample from the terminal node distribution. And then we keep/reject that tree based on its performance. So based on the posterior shape, we can evaluate how well it will do. And then based on that, so we feed in test data. We feed in the test data, and then for each of the tree models, we see what it outputs. So where the peak of the posterior is, that's the value that will be outputted. And then we average all of the outputs of all the tree models. And that's how we use the posterior. So that's basically how BARTs work. And one thing about the BART is that I think they're only available in R and Java as of right now, so no Python. Okay, so now I'll be going into briefly about a stemming algorithm. So basically a stemming algorithm is just an algorithm that reduces words into their bases. So a really common and simple one, yet effective, is the Porter stemmer. So the Porter stemmer checks if words have a common ending such as oy or ing, and if so, it will remove that suffix. But so if we look at stop word list 1, then we look at the string after tokenization and the stop word list 2. So you can see it combines should, shouldn't, would, wouldn't, could, couldn't, and it reduced them to their base stem form, while also just keeping track of the suffix as well. But the bad thing is that are often under stem. So say you have universal, universe, and university. And if you wanted to reduce all of them to universe, Porter stemmer would not be able to do that. But that's why there's more advanced stemmers known as the snowball stemmer and Lancaster stemmers, and they're really interesting. So I know Towards Data Science has some articles on those that I found pretty interesting. So if you have some free time and want to learn about those are pretty cool in my opinion. And so here's just some really quick code on how to create a Porter stemmer in Python. So Natural Language Toolkit is a Python library that you can use to really easily create a Porter stemmer. So yeah, I found that pretty cool. Okay, so what's the best model? So a logistic regression turned out to be preferable because it had the highest amount of precision, meaning it had the least amount of false positives. Because precision is basically the number of positives which were classified correctly, while recall is the percentage of corrects that became positive. And F1 is just a measure that combines precision and recall to get a metric so that it's easy to compare instead of comparing between two metrics. So since logistic regression had the highest precision, it was deemed the most preferable because false positives are bad. I mean, if you got an email from your dream college saying you're accepted, but the phishing detection algorithm detected it as phishing and put it in the spam. I know I personally don't check my spam often, so if I missed that, that'd be heartbreaker. So that's why it's really important to have a really high precision for phishing detection algorithms. So yeah, and the reason why stemming algorithms are really important, I forgot to mention this, but it's because that they break down emails into words, and it makes it easier for machine learning algorithms to find keywords in phishing emails versus normal emails easier. So yeah, that's why stemming algorithms are useful in phishing detection. Okay, and as for social network malware detection, a support vector machine was used for detecting malware spreading and performed well with a high precision, meaning a low rate of false positives. The project made use of social honeypots to serve as a trap, and basically social honeypots are accounts or places with that purposefully have a high vulnerability. So the attacks try to penetrate vulnerable areas. So therefore, on MySpace and Facebook, they went for the social honeypots. So then, after the cyber attack was attempted, the hacker's data was analyzed and stored, and with enough data, the support vector machine was trained. So on MySpace, it was 388 legitimate versus 627 spam, while on Twitter, it was trained on 104 legitimate, 61 spam, and 107 promotion. And the algorithm had 70% recall for MySpace and 82% recall for Twitter.
Machine learning is also important in other computer security fields, such as cryptography. There were these two researchers called Yu and Cao who created a system that uses two synchronized Hopfield neural networks. These are impossible to decrypt without a perfectly synchronized neural network, and because Hopfield neural networks are nonlinear in nature. The output vector created by both of these networks are used as a key to encrypt and decrypt the message, with an extremely hard chance of another person being able to intercept and decrypt the message. So, Hopfield neural networks were designed by a guy named John Hopfield. It's a recurrent neural network that converges on a minimum energy. It contains binary nodes which are either positive 1 or negative 1 and are represented by the state variable. And they have weights connecting each of these nodes. During the update process, two connected nodes would like to turn on and become positive one when the weights between them are positive, and they would like to be negative one when the weights between them are negative. So this is shown by the update function. It calculates the sum of all the products and the weights, and if it's greater than the previous threshold, which is indicated by theta, it updates the state to positive 1, or else it'll update the state to negative 1. After doing this in synchronization multiple times with both neural networks, it'll approach a minimum energy, and after it approaches the minimum energy, the state of all the nodes will be used to create an output vector, and that's what is used to create the key. That's what makes the Hopfield neural networks really good at cryptography, is because the key doesn't travel between both the Hopfield neural networks. However, it's just learned and learned from both the Hopfield neural networks individually. However, one con of these networks are that the minimum energy is very predictable, and it's really bad from a cryptographic point of view because people can just find it easily. That's why people use clipped Hopfield neural networks, which creates more randomization and a larger, more stored patterns that can only be understood by the other clipped Hopfield neural network. Another topic I would like to talk about today is network intrusion detection systems and how you could use machine learning in them. So basically, network intrusion detection systems are systems that detect and try to stop network attacks such as DDoS, which is distributed denial of service attacks, R2L, which is unauthorized access to the network, U2R, which is unauthorized access to the root machine, and other attacks. Network intrusion is part of a broader topic of intrusion detection systems, which such as host-based intrusion detection systems and network-based intrusion detection systems. So the difference is that network intrusion detection is used across the whole network at a few key spots to analyze all the traffic incoming and outgoing from the network, while host intrusion detection systems are used on each host within the network to detect if there's a problem internally and if a virus can be spread through the host. So today I'm only going to be talking about network intrusion detection systems because it's more widely used and it's used to identify attacks in real time, which is why it needs machine learning to make these quick decisions. Network intrusion was a previously hard aspect of cybersecurity to automate because previously there were a lot of false positives and false negatives, and it wasn't really as accurate. However, due to the more powerful processors recently, it increases the capability of these systems and allow machine learning to be used. So some models that they use in network intrusion systems are k-means, Bayes networks, random forest, and neural nets, which is stuff we've all learned before. However, the problem in cybersecurity is that we can't just plug in these models and expect it to work, because we must defend the network from attackers being able to exploit the fact that they use machine learning in their detection systems. The problem with using these models in networks is that the learning mechanism of these models can be exploited. For example, first the attacker can understand the learning method of the model, discover what its flaws are, and exploit those flaws, such as a specific attack that can't be discovered through the model. Another way the model can be exploited is by feeding the machine learning small problems that don't do anything by itself, but it teaches the model to understand it and treat it as normal. And then after a while, after it treats all the malicious data as normal, a hacker can easily breach the system and hack into the network without being detected. These methods have been exploited, but there are some strategies that people use to counter this. So one example is they have two machine learning networks, one that's trained on the training data and doesn't learn from new data, and they have one that continues learning. So basically, even if the machine learning model that continues learning thinks that the activity is fine, it double checks with the old model that's only trained on the training data, and if it disagrees, it still just rejects the incoming request to access the network, and it greatly reduces hackers exploiting the models. This works very well in reducing the numbers of false negatives, which are hackers that get into the system, but the number of false positives, which are like normal people not being able to get in the system, also increase because the network is more secure. However, many companies still use the approach because the benefits of losing the couple of hackers are way better than the cost of losing a few of the members trying to access the network. So another thing I want to discuss is pen testing, which is a common method used by experts in the cybersecurity field to test their own network and find the flaws within it. Basically, they attack their own network. The problem with pen testing currently is that it has a high cost in time and skills required, and because attacks are becoming more complicated and more advanced, the number of people who can perform pen testing are becoming scarce, so they need to start automating it. So previous solutions to this, to automating it, is using partially observable Markov decision processes, which is a way that needs to know the whole configuration of the whole network and designs the best policy and best way to find the flaws. Basically, they create attack graphs, which are nodes that are each part of the network. So each node is like a host computer, the operating system, the other parts of the network. And these nodes are connected by edges, which are called exploits. And by combining exploits that lead to the core of the network, an attack path is created, and they need to find a way to patch it. However, the problem with this is it requires full knowledge of the network, and it's very infeasible for pen testing. And it was a very computationally expensive method. So researchers started to try a different type of method, which uses a combination of Markov decision processes and reinforcement learning, which can help automate it. It solves the problem of needing to know the whole network and host configurations, and all it needs to know is the set of actions that can be performed, the set of rewards that can be achieved, and the current state. So basically, MDP, or Markov decision process, is a framework that is used to create and make decisions with uncertainty. It contains SART, which are state, action, a state space, an action space, a reward space, and a transition space. The state space performs an action that either transitions to another state or gives a reward. The goal of an MDP is to find the best policy that maximizes the reward. The problem with using MDP by itself is it doesn't use the environment of the specific network to make its decisions, and it needs an algorithm to help find the best policy. This is why we use reinforcement learning to find the optimal path within a Markov decision process. I'm not going to go too in depth about the specific network and the cybersecurity details, because we're in machine learning and we're not in cybersecurity, and we only want to understand the use of machine learning. I skipped over some of the stuff talking about how they've made the virtual network to test the reinforcement learning on, because it doesn't really matter. But as you can see, here are a bunch of states, a bunch of actions, and a bunch of possible next states, which are the results of the actions. The specific RL model is going to use QLearning, which is a type of reinforcement learning where the Q of an action and a state results in the maximum expected reward. And the method that the QLearning uses to choose its action either uses greedily selects it, or uses an upper confidence bound to select the action to explore. So after it explores each function, each action, and each state, it'll update the Q function, and it'll converge on an optimal reward for each state action pairing. The reward uses alpha, which indicates the learning rate and how much it changes based on each exploration, and it has gamma, which controls how it values Immediate rewards versus long-term rewards. After it finishes learning, the RL will be ready for pen testing on the network, and it finds the best policy. Researchers have looked into combining this QLearning model with other models such as neural networks and deep networks to create something called a deep Q network, which is way stronger and will be way more efficient if you have a really large network and you need to find more patterns. So yeah, that's our lecture. Thank you for listening. If you have anything or any questions about this lecture, feel free to message us or put it in the chat. Thank you for listening to our presentation.